today we're going to start with what we decided to label as single source inference. And we're going to have 4 talks on the subject. What we mean by single source inference is not really you have a single binary. So for example, we're going to have talks about how to analyze something like a stochastic background. So what we mean here is mostly the first stage after you get some data, how you actually do the first pass through the data and look for a common origin of your signal. And I'm not really going to give you an introduction to this because we have 4 talks that will discuss all aspects of this topic. But I just wanted to very briefly, in 5-10 minutes, try to give some sort of common picture of what we'll talk about today. So what we'll talk about today, like I said, is how you go from raw data, and the raw data can be whatever. If you have an interferometer, you have strain, like on the right for LIGO. If you have pulsar timing, that we'll have a talk from Sarah Vigeland later, you actually have time of arrival from pulsars, and that's your raw-ish data, as hopefully as raw as you can. And from that, how you go after a first pass through the data, how you go to some inference about basic properties of whatever signal you're seeing, and also statistical detection, detection claims, and how you express those statistically. So though not everyone will use exactly the same framework, exactly the same words, something that personally helps me understand these different types of signals and these different types of experiments and detectors we're using, trying to break this down to the most basic terms and basic assumptions that go into this. And at least the way I try to picture the process for all those instruments is actually there's a lot of common methodology and common assumptions. And whatever inference scheme is going to be some variation, whatever inference scheme people use is going to be some variation of this. Sometimes things are more, the assumptions are different. Sometimes the computations are exact. Sometimes they're not exact. But more or less, everybody uses some sort of a logic related to this equation, where you have different terms. You have likelihoods, priors, evidence, and posterior. We might use different words in each experiment for those terms. But ultimately, they have some common characteristics. So for example, in any case, the likelihood is going to be based on assumptions about the detector and the detector noise. So in every case, when I have gravitational waves arriving at a detector response in some way, all these are going to change from experiment to experiment. What kind of signal you're talking about, what kind of response you're talking about will change from experiment to experiment. But at the end of the day, everyone will more or less construct a likelihood function based on the noise model in the detector. And the noise model will be different, but at the end of the day, this is what the likelihood function is. And this is what I like keeping in mind whenever somebody talks about their likelihood function. Besides their noise model, everybody will have some sort of prior, and I like thinking about it a little bit in terms of like a signal and response model, what the signal you're observing is and how your detector responds to this signal. For LIGO that measures strain, the signal model is something like a waveform that we'll talk about a lot more on Friday in the context also of systematics. But if your signal is actually a stochastic background, then maybe your signal model is the power spectrum of this background, and expressed here on the bottom for nanograph through actually the correlations, the cross correlations between the different detectors, which in this case is pulsars. For the common case of CBCs, we'll talk about this a lot more tomorrow. So for the common case of CBCs, the signal model ends up being what happens in a compact binary, parameterized in terms of a number of parameters that you have to set priors for, and how to deal with those in a systematic way. It will be the topic of tomorrow's discussion. One thing that I would like to try to keep in mind while I watch the talks personally, because I find it interesting, and maybe also address in the discussion session, has to do with the response of your detector and how you take into account uncertainties in the response. Here's, for example, one approach of what LIGO does, which is to take your waveform and add a small perturbation over it, some amplitude and some phase that accounts for your uncertainty in how the detector responds. So this is something that I think would be interesting to keep in mind and address for the different experiments we're discussing today as well. You have this term that I'm going to boycott, and then you have this term. Finally, this is more or less going to be the end point for today, and tomorrow we'll take a step further. But this term tells you the information you need about whatever created the signal you're observing. Here's an example of such a posterior. Here's the masses of GW 170817. The details don't matter, but the usefulness of a plot like this is that it tells you what the possible masses of the system that created the signal you're observing are. M1 and M2, the two masses in the binary. And the final thing I wanted to say before we go into the details with our 4 talks is that when I see plots like this, I also like having a secondary read to them besides what the probable values for the parameters of the system are. And it's that if you know nothing about gravitational waves, you know nothing about neutron star binaries, looking at a plot like this already tells you a lot of things about the system besides just the numerical value of the masses. It tells you, for example, that there is a parameter combination, there's a mass combination that is measured extremely well because this parameter must affect the signal very, very strongly. And of course, from gravitational wave theory, we know that there is a Chern mass parameter that drives the in-spiral. We know that the different parameter combination, the mass ratio is a sublating effect. We don't measure it very well, so it cannot affect the signal too much. And we also know that the mass ratio and the spin of the system have similar effects, because if you change assumptions about one, then your inference about the other parameter changes a lot. So you know that physically they have to be related to one another, and they must have similar effects in your signal. Okay. So I'm going to stop here, and we're going to have 4 talks where people will hopefully tell you that this is all a very simplistic picture. In reality, there's tons of complications. And let's see if we can break down this simple classification I have here. So we're going to start with Tyson Littenberg remotely talking about LIGO.